Hi, applied students. Today we're going to take a look at distinguishable permutations. Now, we've already talked about counting principles. We've looked at the idea of permutations and factorial notation. Today we're going to take it one step further and take a look at distinguishable permutations. So, let's evaluate. Now, how would we find out what 6 pick 2 would be? Okay, what does that mean? That means we have 6 objects, any 6 objects, and we want to place 2 of them in order. So if we take a look at this, what would that be? Well, that would mean that we'd have 6 choices for the first object. And because we picked an object, we'd have 5 choices for the second object. 6 times 5 would tell us that the answer would be 30. Okay? Now, or we can use the calculator to help us. If you have your graphing calculator here today, here's how you're going to use the permutations and the combinations button on it. There is a permutations and combinations button on normal scientific calculators, but I'm only going to show you how to do it on the graphing calculator for now. So if you brought it, great. If not, well, then I guess you should have brought it, right? Huh? Another advantage of making sure you're bringing your materials to class. So, 6 pick 2. Here's how we do it. You type in 6. Then you go to the math menu. At the math menu, go to probability and pick a second option there, which is NPR. Press enter, and then press a 2 for 6 pick 2, and then press enter. And as you can see, the answer is 30. So if we're doing that on the calculator, we also get the answer of 30. Let's try that for 5 pick 5. 5, math menu, probability, option 2, 5. The answer is 120. So, answer equals 120. Now let's take a look at an example. In order to access a website, Robert must choose a 4-digit number, a 5-digit number, or a 6-digit number. He cannot choose the same digit twice in his number. How many different numbers can Robert choose? So we'll take a look at all the different options. We've got a 4-digit number, a 5-digit number, and a 6-digit number. How many digits are there to choose from? Well, you can have 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. In other words, there's 10 digits to choose from. So it's going to be 10 pick 4, 10 pick 5, and 10 pick 6. Let's figure out what those are. 10 pick 4, 50, 40. 10 pick 5. So I'm going to cheat here and just go second entry and erase that 4 and put a 5. I get 30 to 40. Makes sense. There's more numbers, so greater numbers options. How about 10 pick 6? Make that 6, and we get 151,200. Now, if we're going to add those bad boys together, we're going to get 181,000. How about 186,000? And 480. That's the number of codes that Robert could choose. Keep in mind that when you're choosing a password, that's why websites might give you a variety of options. Because the more options they give you, the more passcodes that are possible and the harder it is for someone to guess your passcode. We'll do another example. Mr. Hutton has 5 dogs: Abby, Mika, Sam, Sophie, and Gracie. How many ways can the dogs have their picture taken in a line if Sam, Sophie, and Gracie are beside one another? So This is a very classic type of permutation or counting question. You have a bunch of things in a line, and things want to be beside one another. Here's how we have to treat it, okay? We have to look at this as what it is. We're going to call Sam S. We're going to call Sophie P, Gracie G, Abby A, and Mika M. If we take a look at what this is we can have Abby here, and then we can have that SPG unit here, and then we can have Mika here. All right? But I guess we can also have SPG here, Abby here, Mika there. Or we can have SPG here, Abby here, Mika there. In each of these three possibilities, Abby was to the left of Mika. Of course, the reverse is also possible. Mika could be to the left of Abby. So it could be M, SPG, A, SPG, MA, or MA, and then SPG. So what we can see here is that there are exactly 6 possibilities of arranging Abby, Mika, and the 3 dogs. However, what we did not consider at all is the number of ways of organizing Sophie, Sam, and Gracie. Now, in each of these, in every single one of these 6 outcomes we have laid out, there's going to be a number of different possibilities based on the number of ways of arranging Sam, Sophie, and Gracie. So, how can we take a look at them all? Well, really, we just have to look at how many ways can we arrange Sam, Sophie, and Gracie. So let's take a look at it. Because really, in this particular example, it's not a lot different than what we've already done. If we take a look at it, Sam can go here, Sophie can go here, Gracie can go here. Sam could go here, Gracie could go here, Sophie could go there. Sophie could go here, Sam could go here, Gracie could go here. Sophie here, Gracie here, Sam here. Gracie, Sam, Sophie, Gracie, Sophie, Sam. How many possibilities did we list? 1, 2, 3, 4, 5, 6. Understand the implication. There are 6 outcomes in every single one of these. Every single one of these original 6 outcomes has 6 outcomes embedded in it because there are 6 different ways of arranging Sam, Sophie, and Gracie who want to be together. Now, understandably, you're not going to want to have to write this out like this every single time you do a problem like this. So, what is a more elegant way of doing it? By the way, this is a beautiful solution. It completely maps things out and it shows a clear understanding of things. And I'm not trying to discourage you from using it. Rather, I'm going to try and show you a nicer way of doing it if you have a strong hold of combinatorics. So what I'm going to do here, you notice I didn't say what the answer was yet, but it should be pretty clear what the answer is because there's 6 outcomes in each of 6 outcomes. So there's 36 altogether. Now, what we're going to do here, so I'm going to erase all this. I need a big eraser. And we're going to start this question from scratch because now I'm going to do it using factorials and permutations. Here we go. Because here's the idea. And now you've seen the theory behind it, but here's the idea. You have 1, 2, 3 things, right? One of these units is Abby. One of these units is Mika. One of these units is the 3 dogs. Now, we have 3 things we're trying to order. those three things can be ordered in 3 factorial ways. Then, the 3 dogs, Sam, Sophie, Gracie, who need to be together, they can also be arranged in 3 factorial ways. 3 factorial is 6, so 6 times 6 is 36. A lot less work, as long as you understand what's going on. Okay? And there we have it. Part B. Gracie cannot be in the middle. 1, 2, 3, 4, 5 dogs. Now nothing else is happening here. Sam, Sophie, and Gracie aren't together. The only thing that needs to be considered is Gracie cannot be in the middle. If Gracie can't be in the middle, then there's 4 dogs who can go in the middle. Once you place one of them, there's 4 left to choose here, 3 left here, 2 left here, 1 here. So in other words, it's 4 times 4 factorial. 4 factorial is 24 times 4 is 96. There's 96 ways of placing the dogs in such a way that Gracie cannot be in the middle. Part C. Abby doesn't want to be beside Sophie. How can we do this question? Well, here's what we have to consider. Instead of them being together, they can't be together. So the first thing that we have to do is consider the easiest way of doing this. The easiest way of doing this is looking at the total number of outcomes with no restrictions and subtracting the number of outcomes where they are beside one another. Because if we know all the number of times that they are beside one another, then all the rest are going to be when they're not. So we'll start off with the total number of outcomes. Total number of outcomes with no restrictions is 5 factorial. 5 times 4 times 3 times 2 times 1. So there's 120 ways of placing the dogs. Next, how many ways would they be together? If they're together, then you have Sam, you have Sophie and Abby. Actually, we called her P before, so I should call her P just to keep things consistent. Then we have Mika and we have Gracie. So even though they're together, we consider that as one dog. So we have 1, 2, 3, 4 dogs to arrange, so that's 4 factorial. Then, because we have 2 dogs in this unit that's together, we'll multiply that by 2 factorial. 4 factorial is 24 times 2 is 48. So there's 48 ways. That is the total number of ways. And there's 48 ways where the 2 are together. So to figure out the number of ways in which they are not together, you merely take the total number of ways and subtract the number of ways where they are together. And you get 72 ways. The homework is in your textbook. It's questions numbers 1 to 18 on pages 255 to 257.